All right, so today we're doing DC circuits. What does DC mean?
Direct current.
Yeah, direct current circuits. And here's one of our goals. So what we'll have is circuits like this. By the way, so let me remind you of Ohm's law first before I get into that. So here's a battery, voltage V. Here's a device, heater, bulb, or something like that, characterized by this resistance. And what is the current in this circuit?
Voltage divided by resistance.
Right, so I is, and this is Ohm's law, okay? Now, one of the goals in this chapter is the following, one of the main goals, in fact. So you'll have circuits like this. They'll have multiple loops and multiple sources, okay? And you want to find the current in each device. So just with Ohm's law, you couldn't do that. All right? If you can't solve a problem with the existing laws, what do you do?
Make a new one.
Make a new one. All right? And these Kirchhoff's rules are two new rules to help you solve these guys. Why do we care about a current in a device?
It determines how much work can be done by it.
All right. So it tells you how bright it is glowing. The power consumed by this device is I square R. Okay? So we want to know how bright or how much work it's doing, how fast it'll cook your pizza, and all that kind of stuff. All right, so our goal, the main goal in this chapter is to find the currents in each element. And that's called solving the circuit. Okay? So, for instance, so in a circuit like this says, how many loops does this circuit have? Two, three. 1, 2, 3. Okay? And this is called an arm. This is called a junction. When more than two arms meet at a point, that's a junction. Okay? The current in a given arm is the same. Okay, so the current in this guy and this guy is the same. The current in this arm is that. The current in this arm is I2. Okay, so solving this circuit means finding the current in the three arms. If you call them X, Y, Z, you have three unknowns, and that's what you want to find. So, okay, so that's what this chapter is about. All right, so you guys understand where we're headed? All right, so let's start. So here's a device that many of you might have used. And what does this guy do? And this circuit is in there. It's an amplifier. What is an amplifier? So the signal, electrical signal coming in there is like that. What needs to be fed to the speaker needs to be a little larger to produce sound that you can hear. Okay, and that's the job of this guy. Okay, to maintain fidelity and to increase the amplitude. Okay, so maintain fidelity meaning?
Clarity of sound.
Maintain the shape, so the frequency content. Okay. All right, looks like this guy has more energy than this guy.
Means you gotta add energy.
Right. So there was the battery. Okay. So it was drawing energy from the phone itself. All right. All right. So again, when we're not going to do anything like this, but you would need to know the current through all devices and stuff like that. Okay. All right. So you saw this diagram. Here's a simple circuit, and you saw that the potential. So we'll think of this as a positive charge going around like that. But in reality, what is it that's happening? It's electrons moving from here to there. Okay. All right. What this diagram shows you is the potential energy of the positive charge. Here it's high, and then it loses potential energy as it goes through the load. Okay? And that potential energy is converted to whatever it is that this load is doing. And then here it's lost all its potential energy. The battery spends chemical energy and gives the charge back the potential energy, and it can go do its stuff again. The EMF for the battery, you'll see the voltage of the battery is written as EMF of the battery. That's another term used, is maximum voltage that the battery can provide. Okay. So you'll see that when you go buy a car battery, let's say, what's a car battery? What's the voltage of a car battery? 12 volts. When you buy those little batteries, that's 1.5 volts, 9 volts, and so on. Okay. Now, generally, you don't get to see all the 12 volts or whatever. Okay, here's what happens. Here's the battery, and here's the symbol for the internal resistance. Internal resistance is denoted by little r. Okay. So let's say, well, you connect a load to the battery, and the current will depend on the load. Okay. And if the load is much, it'll depend on the load and the internal resistance. Okay. And the current in the circuit, current is the voltage divided by the total resistance. Okay. All right. Now, the voltage that you see outside the battery, okay, so you'll understand this in a few minutes, is when you go from here to there, the voltage changes plus E, and then current flows from a higher voltage to a lower voltage. So the change in voltage across this element is I times R. So E minus I times R, that is the voltage you see, okay, outside the battery. So if this was a 12-volt battery, you don't see 12 volts, you see this much less. So when a battery dies, what happens? You're not.
All the chemical reactions are done.
Yeah, so you're not seeing any voltage, so you can think of the internal resistance as going to infinity, and this has become zero. Okay, so the terminal voltages. And then if it's a rechargeable battery, what does a rechargeable battery mean?
Allows you to put electrical energy back in chemical energy.
Yeah, so the chemical reaction is reversible. Okay. So if you give energy, the reaction will go backwards. Okay. So lithium-ion batteries, you can recharge them about 500 times. Okay. So the current in the circuit is that over R. Okay. By the way, so again, you guys need to understand terminal voltage. Terminal voltage is the voltage you see outside, okay? And it's the EMF of the battery minus I times R. And I, of course, will depend on what the load is. So the terminal voltage will be different depending on what it is that's connected to the battery, okay? And you will see this in lab when we do lab, these labs either this week or next week or something, okay? You'll see them. All right. So the current in the circuit is EMF of the battery divided by the total resistance, and the resistance is, for a series connection, it's just the sum of the resistors. The power delivered by the battery is the EMF of the battery times I. I is, and EMF is I times R, so power can be written as I square R plus R. And that's equal to I square R. Okay, what is this guy?
The current squared times the resistance of,
That's the power delivered to your oven. That's what's cooking your pizza. What is this guy?
internal resistance.
Yeah, so that's being wasted as heat inside the battery. Yep. All right. All right, so here are resistors connected in series. Okay. So this is how those string of Christmas lights are connected. What's the problem with this connection?
Oh, for every additional string you attach, the less power to each light.
Okay, when one of these bulbs goes bad, the whole string went bad in the old days. So what was the workaround they found?
Put them in parallel with each other.
No, they're still in series. So this was a genius workaround. So the elements were like this, and this would burn. And now, as they burn, what happens is this wire bends, and they make an electrical connection. Yeah.
What was the reasoning to put them in parallel?
What's that?
Like, why did they just not put them in parallel to begin with?
If you put them in parallel, okay. Well, you would use a lot of wiring for stringing. All those wires have to come to the plug. A series connection, you use little wire, a lot less wire. So if this were 100 bulbs with a parallel connection, you would need a wire 100 times the length of the series connection. All right. So, yeah, go check your string of wires. It's really a very cool solution. Yeah. When your resistors connected in series, the equivalent resistance is just the sum of the resistances. When resistors are connected in parallel, okay, so here's the parallel connection, and the equivalent resistance is the sum of the inverse sum. So inverse of the equivalent resistance is the inverse sum. And you see all these guys are positive. So this term has to be the largest, meaning this resistance has to be the smallest among all of them. So when you connect a bunch of these guys in parallel, the equivalent resistance is smaller than the smallest one of those. Okay, what's the advantage of this parallel connection?
The voltage across both is the same.
The voltage across each element is the same. So in your homes, every plug is a parallel connection. Every device is a parallel connection. If something goes out, the rest of the house is not hobbled. Yep. In fact, homes are connected in parallel. Let's say something destroys this home, all the other homes can still function. Yep. All right, here's a interesting problem. I've known this for a long time. Okay, essentially, so imagine each one of these resistors is a 1 ohm resistor. Go try this at home. So it's an infinite ladder. 1, 1, 1. What you want to find is what is the equivalent resistance. Okay, I'll give you a hint. Okay, so to this one, this is connected in parallel, and it makes it smaller than 1 ohm. And then this would be in series, so this would be 1, 2, and something smaller than 1 ohm. So the equivalent resistance is between 2 and 3 ohms. Okay. And if you solve it on your own, I might even buy you a soda. All right, so here's the main goal of the chapter. We want to solve the circuit. And what does solving the circuit mean?
Identifying current at every point.
I'm sorry?
Identifying current at every point,
Every point,
or every,
device. Right, every load. And so that'll tell us how bright that device glows, okay, so to speak. Now, the rules are fairly simple, okay, and what this is, the first rule says, the current rule says, the current flowing into a junction is equal to the sum of the currents flowing into the junction is equal to the sum of currents flowing out of the junction. And that makes sense because you have charge doesn't collect at any point. So and think of water flowing. The water flowing into a junction is equal to the water flowing out of the junction. Okay, so that's what this rule is saying. So this is the current flowing into the junction, and that's equal to the sum of the currents flowing out of the junction. And here's the second rule, the voltage rule. And before I tell you about this, let me do an analogy. So here's a mountain, and let's say you're going for a hike on the mountain. Yeah. So you do the hike in multi-steps, and you come back to your starting point. What is the total elevation change on this hike? 0. Okay. And so that's this voltage rule. Okay, so if you go around a closed loop, the sum of the voltage changes across each device must add up to 0 when you come back to the starting point. And that's the voltage rule. Okay? So between these two rules, and in fact, you'll do a whole circuits class just based on these two rules. Again, that'll be the foundation for your circuits class. Okay, finding currents through all kinds of devices and stuff like that. Okay. All right, so when you apply this voltage rule, so here's what you want to notice. Okay, so in this loop, how many devices are there? 1, 2, 3, 4. So when you write this, there'll be 4 terms. The sum of 4 terms equal to 0. When you go around the loop like this, 1, 2, 3, 4, 5, 6 terms. Okay, and so on. Okay, so again, these are the two Kirchhoff's rules. The current rule tells you that current flowing into a junction is equal to a sum of currents flowing out of the junction. And the loop rule says around any closed loop, the sum of the voltages across each element should add up to 0. Now here are some of the rules that you have to know. So if this is a resistor and current is flowing in this direction, current flows from a higher voltage to a lower voltage. So when you go in the same direction as the flow of current, you're going downhill. Okay? So the change in voltage when you go across is negative I times R. Okay? When you're going against the current, you're going uphill, so the change in voltage is plus IR. Okay, so remember that. And it's useful to think of the current as water flowing. Okay? When you're going with the water flow, your elevation is decreasing. Okay? Voltage change is negative, and when you're going against the water, you're going uphill. All right. For a battery, when you're going there, you're going from low to high voltage, so the change in voltage is positive. And when you're going from positive to negative, change in voltage is negative. Okay, so to solve this circuit, we need to know the current in this arm, and that arm. You have three unknowns, and so you'll need three equations. And how are you going to get the three equations? Well, you just learned two new laws, and these are the ones that are going to give you three equations. Okay? This guy is easy to use, so you always want to use this one first. Okay? And this is a little more complicated, but it's not that bad. All right. So to solve this equation, what you need is three equations. Okay, here's one junction, and here's the other junction. Okay. Now, if the junctions are across the same arm, they'll give you the same equation. Okay. So you apply the junction rule, and so what is the current flowing into this junction? I3. So I3 is flowing in, and I1 and I2 are flowing out. Okay. How many loops are there? Three. Okay, so 1, 2, 3. So you can choose any two of three, because all you need is two more equations. Okay? All right. I'm going to write the equation down. I'll call this loop 1, and I'll use loop 2. Okay. Loop 1. Okay, so I'm going to start from here and go around the loop like that. Okay, so I'm going to start here, go around the loop, and come back here. By the way, before we do that, how many terms will be there? 1, 2, 3, 4 terms in that equation. Okay. So first term, I'm going uphill. So it's plus I1 R1. Then, can somebody help me out here? I'm going to go across this internal resistance.
Plus I1 little r1.
Yep, plus I1 little r1. And then,
You're going from high to low, so it's negative, so minus u1.
and then plus I3 R3. Okay, so this loop gave you another equation. All right. Loop 2 is going to be this loop, okay? All right, we'll start here and go around like that. Anybody want to help me?
I1 little r1 minus u1, then that's going to be negative I2 little r2 minus u2, and minus I2 big R2 plus I1 big R1.
Okay, so there you go. You have three unknowns and three equations. Okay, that's how you'll solve this problem. Okay. And like I said, That's the foundation for an entire circuits course. Has anybody here done a circuits course yet? All right. So now that we bought a new hammer, what's our job?
Hit the
Huh?
nail. Hit the nail.
Yeah. So go use it. All right. So here's where we'll first use it. Okay. So this is called an RC circuit, R being a resistor and C being a capacitor. Okay. All right, so here's our capacitor, here's our resistor, there's a switch. Okay, here's our battery. Okay, what we're going to do is we're going to close the switch, and what is going to happen?
The capacitor is gonna charge.
The capacitor is going to charge, so energy is going to flow from here to there. Okay, and once the capacitor is charged, we'll use it for whatever it is that we use. Okay, so how long do you think the capacitor takes to charge?
Not very long.
No, not in this instant. Remember, this guy doesn't give up his energy fast. So on your flash camera circuit, when that light is blinking amber, that's being charged. So it might take you a second or two or three or whatever. Okay. You can discharge it fairly fast. Okay. So what we're going to do is, okay, we're going to close the switch, and we want to understand the behavior of this circuit for the second or two it takes to charge the capacitor. Okay, so things are changing, and we want to know how things are changing in that 1 or 2 seconds or 3 seconds, however long it takes the capacitor to charge. So here we go. Okay. So what we're going to do is, okay, so here we close the switch, and now you can see that this is a closed loop. We have our hammer. What did Mr. Kirchhoff tell us? The sum of the voltages across all elements in a closed loop add up to 0. That's our hammer. Okay, so we're going to do that. So let's start here. We'll go across this. That's plus E. This is the charge on this is Q, and by the way, this charge is QT. So it's a function of time, and that's what we're interested in finding. Okay. So it's minus QT. You're going from high to low. So minus Q over C. Remember, capacitance, charge, and voltage are related like that. So voltage across a capacitor is the charge on the capacitor divided by C. So that's that term. And then you go across this, and you're going with the current, so it's minus IR. Okay, so in this system, so there's the equation, and E is QT by C, I is dQ by dt. So we'll pause here a second and make sure we understand this, because here's a very important thing. All right, so here was a system. Okay, we wanted to study the system, and what is an easy way to study? How can you study the system? You can go set up the system in lab, spend many hours studying this, making measurements, spending expensive equipment. Or here's the system. You put in a physical principle, and what you get is a mathematical model. This is your mathematical model. What is your mathematical model telling you? That this guy, the charging of the capacitor, obeys this differential equation. Yep. And this is easy to solve. You guys are all experts at differential equations. Okay, so this is a general theme. You'll be interested in studying systems, and you use some kind of principle to come up with a mathematical model and then solve the differential equation. And more often than not, the mathematical model is a differential equation. All right, so you can solve this differential equation, and here is the solution to that differential equation. Okay. So the charge on the capacitor builds up exponentially, okay? And the time constant is RC, okay? RC, that controls how fast the capacitor charges, okay? You want to charge it fast, what do you have to do? Decrease the value of this resistance, yep. What is the price you pay if you want to charge it fast?
You lose energy to the. You lose energy to the.
Well, large currents would maybe burn wires and stuff like that. Okay? So, all right. So here you see this is a slow charging. The time constant is 2 seconds. So this is taking 4 or 5 seconds to charge. What happens is in 2 seconds, 65% of the charge is built. Another 2 seconds, about 90% of the charge is built. 65% of the remaining charge, and so on. Okay. So that's how the charge is building. Okay. Current as the capacitor is being charged. So when you first close the switch, the current is maximum. Okay. And then the charging gets slower and slower. So the current in the circuit decays exponentially. Okay. As the capacitor is completely charged, as the capacitor gets to full charge, the current is dying down. Okay. All right, so I'm just going to review this stuff one more time. Okay. Here's the system you wanted to study. What is it that we were studying? You close the switch and you wanted to study how's the capacitor being charged, okay? And how long is this phenomenon lasting? Essentially just a few seconds, okay? So you're studying how you're trying to find this function. How's the charge on the capacitor building up as time? And so here was your system. You put in a physical principle, came up with a mathematical model, and there's your mathematical model. And your mathematical model for the behavior of the system generally is a differential equation. Okay? So the charge on the capacitor satisfies this differential equation, and you know how to solve that differential equation. Here's the solution. Okay. So now that you have that hammer, you're going to use it everywhere. Okay. So okay, so in the previous example, what we did was we studied the first part of this equation. You close the switch and you charge the capacitor. And now what we're going to do is, we've charged the capacitor, we're going to open the switch, and now we're going to use the energy stored in here for whatever it is that we're doing. If this is a flash camera, you take a picture and this flash bulb goes on. If this is a defibrillator, you want to jump start somebody's heart, close the switch and give them a shock and restart the heart. Okay. If this is a pacemaker, this is part of a pacemaker circuit, you close this switch and start their heartbeat. Okay. So now we're going to discharge this capacitor through our load. Okay. So the capacitor is fully charged. We're going to close it, and we're going to, so as soon as you close the switch, there's going to be a current this way. And what we want is, how's the capacitor discharging? We want to know this function. Okay. So here's your system. What are you going to do? Are you going to run to a lab? No, we know differential equations. So we're going to set up a mathematical model. What is the physical principle that is going to go? Kirchhoff's laws. Okay. So here's a loop. Okay. The sum of the voltages around the loop should be 0. There's only 2 terms. Okay. So we're going to go around the loop like that. Minus, so we're going to go from high to low. So minus Q over C. So I will explicitly write the time dependence there. Okay. And then you're going against the current. Okay. So it's plus IR. Except that here you have to be careful. I, the current, see what is happening as the capacitor is discharging, what is happening to Q? Q is decreasing. So I is minus dQ by dt. Because dQ by dt is negative, Q is decreasing, and so I is negative dQ by dt. Okay? So there is your differential equation. Okay? All right? And you can solve this differential equation. Okay? And there is the solution to this differential equation. Okay, so the charge decays exponentially, and there's the time constant again, RC. Yeah. RC is the time constant. Okay, so if you want to discharge the capacitor fast, you make R small. Okay, so this is your control. That's how you control how fast you discharge the capacitor. Okay? If you want a fusion reaction, that's very small. Okay? So you're firing those lasers very fast. Okay. If you are, you're starting a heartbeat, needs to be a fraction of a second and so on. All right. So the capacitor discharges exponentially, and the current also dies exponentially. Okay. Current is just the time derivative of that. So in this case, it's minus dQ by dt. So here's a pacemaker. Again, what is a pacemaker?
Artificial heartbeat.
Right. So if your heart doesn't beat in regularly, if the circuits in there misfire, you're going to start the heartbeat. Okay, you're going to control it. And here's how you're going to control it. Okay. So here's the battery that's implanted. Okay, and when the so when the switch is open, okay, I'm going to show you a simpler circuit first, and then we'll come to this one. Okay. So the simpler one is okay. So you're going to close this switch and the capacitor charges. Yep. And then you'll open the switch, and when you want to start the heartbeat, you close the switch. And the capacitor discharges through your heart, and it starts the heartbeat. All right, so you set these values such that, okay, you set this value, let's say you want heartbeat, you want your heart to beat 60 times a minute. So the charging process happens in, let's say, 0.8 of a second or whatever. Yeah. Once it's charged, then you fire it. Okay? Firing doesn't take too long. So you set the R values such that it's charging in less than a second, so you can fire the heart. What if you want to go for a run?
You lower the resistor even more.
What's that?
You lower the resistor even more.
Yeah, so you want to charge this faster. Let's say now you want 120 beats per minute, so you want the capacitor to charge in half a second. Okay, so you need to come up with a way of making this resistance adjustable. Okay, how are you going to decide that? When you go for a run, you're starting to breathe faster, and your breathing rate will control the value of this resistance. Yep. All right, so that's the simpler form. So when the switch is open, the capacitor charges. Your heart is being just used as a resistor. It charges. And then when you want to fire your heart, you close the switch. Yep. So that's the pacemaker circuit. Okay, so this is the capacitor charging, and then discharges, starts your heartbeat, and then the capacitor charges again, discharges, charges again. So you're setting a regular pattern for heartbeat. So here's an interesting problem. Here's an electric eel, and you might know this. So here's an electric eel. So here's the electric eel. It passes an electric current through this fish. See, seawater is conducting. It passes a current through this fish. The fish dies. Well, this current passed through the electric eel as well. Why didn't it die?
Is a higher resistance than the fish?
The same current is flowing through that. So you guys understand the problem?
Half of the current?
Hmm?
Half of the current?
No, the same current is flowing through that thing too.
No, it's just on its skin of the eel versus center of the fish. Never mind.
So here's how it solves the problem. So here's the diagram. Okay, so here's the current coming out of the eel. It goes through the fish, and it goes along one path. When it comes back, okay, so there are inside the eel, there are several paths, 140 paths. So this current gets divided into 140 smaller currents. And that's how it survives. Okay.
Like in its skin, it has that.
No, through its body. It's
Like better conducting areas of the
Okay, so here's a 1 amp current that'll kill you. That'll kill the fish. And then this once it comes in, there's 100 wires. 100 conducting paths. So each one is carrying 0.01 amp current.
They're just organs that act as like a ground.
So, okay, so let's look at the details now, okay? So, a normal cell in every cell in your body, in a normal cell in your body, the voltage is minus 70 millivolts inside your cell. Okay, so this inside your cell, it's 70 millivolts below the outside voltage. The batteries of an electric eel are electroplaques, each with an EMF of 0.15 volts. So eels have these cells, specialized cells, where the voltage is 150 millivolts, each cell, and an internal resistance of 0.25 ohms. Okay. Eels have 140 rows of electroplaques. These are the specialized cells, specialized battery. Each row has 5,000 electroplaques, 5,000 of these cells. So 0.515 volts plus 0.15 volt and 5,000 of them. That adds up to 750 volts. So that's 750 volts, and there's 140 rows of those. That's a lot of batteries. And that's sending a current of 1 amp. Okay, so the effective voltage and internal resistance of this array is 750 volts and 9 ohm internal resistance. All those guys add up to that. Okay? And then they're in parallel. The eel uses the surrounding seawater to complete the circuit from near its head to tail. Okay. This amount of water has a resistance of 800 ohms. So this water is 800 ohms. So 800 volts divided by 800 ohms is 1 amp current. So there's a 1 amp current flowing in the fish. Yeah. So the eel fires its electric gun only when the fish is close by. What happens if the fish is too far by?
The path of the current doesn't go through the fish.
The resistance increases, the current is smaller. Yeah. So a current of 1 amp passing through a fish swimming nearby can kill it. If the fish is too far away, this current would be smaller. Current in each of the electroplaques itself is 1/40th of this current, which is 6 milliamp. And that doesn't kill the eel itself. I don't know, you might have seen these 3-wave bulbs. So they have 2 filaments. When this switch is closed, you get a 75-watt bulb. When that is open and this is closed, you get a 100-watt bulb. And when both switches are closed, you get a 175-watt bulb. Okay, so the 3-prong plugs, what they do is the following. So you see if this went bad and the wire is touching the housing, that current would go through you, but the housing is connected to a ground wire. Okay, and so the current flows through the path of least resistance. Your resistance is higher than that. Okay, so that's the third prong is for the ground wire. Household wirings are all connected in parallel. So if this one goes bad, this one will still function and so on. and houses themselves in a city are connected in parallel. This is one house, and so on. So heavy-duty appliances need 240 volts. So actually what you're getting is two signals. This is a 120 volt amplitude signal, and another signal that's 180 degrees out of phase. So if you want only 120 degrees, you use this and a ground wire. If you want 240 degrees, you use this and this. And you see the peak difference is 240 volts. Here's how your circuit breakers work. What's the job of the circuit breaker?
Break contact.
Uh-huh. So here's a wire behind the wall, and if too much current flows through that wire, that'll burn, and then you'd have to break down your wall to fix that wire. You don't want to be doing that. So if too large a current flows through this is a bimetallic strip. I don't know if they use these, but here's a way to solve it. They expand differently. Like this guy will expand more than this guy, and this bends like that, and it'll lose contact. So as soon as too much current flows through, the electrical contact is broken. And then the advantage of this is easy to reset. You go to your garage and reset it.
And the breaker part is put in series to whatever outlet it is, right?
Yeah, this is going to your device. Yeah, the outlet. Yep. All right. Now I got a few slides on how your nerves work. If you want to hear about that, I'll tell you. Otherwise, we can stop here.
Sure.
All right. I'll be very brief about it, okay? So what are you?
I am my brain,
Yeah.
my body.
There you go. So you are really 90 billion interconnected neurons. That's your biggest asset. Everything else is an appendage. This is the most powerful computer on the planet. 90 billion interconnected neurons. Okay?
Sure doesn't feel like it sometimes.
Heck, I mean, this is each of our brains is as powerful as a million of these, but I don't even use 5% of the capacity of this thing, All right. Anyway, so you have sensory neurons that bring in input. If there needs processing happens here, and here's the output. Okay. Here's how a nerve impulse looks like. Okay. So remember, what is the? Okay. So here's a neuron. Here's a neuron. So there's inside the cell. Okay. What is the potential inside the cell? So
7 milliamps, or 70 milliamps.
minus 70 millivolts, okay? So everywhere along this thing, it's minus 70 millivolts. And when a nerve impulse is traveling, so this 70 millivolts, there's a nerve impulse. It's become positive, and that travels down the axon. Okay, and we're going to talk about how that happens. Okay. Okay, that's a nerve impulse. Okay, so here's the deal. That nerve impulse, that action potential, so there is a minus 70 millivolts. In that location where the nerve impulse is created, it's become 30 millivolts, and then all this happens. So the length of this nerve impulse is about 3 milliseconds. That's the width of that nerve impulse. Okay. Nerve signals travel along at speeds of about 100 meters per second. So they travel at about 100 meters per second down your nerve. What determines that speed? Here's what needs to happen. I touch a hot plate. I need to be able to react that fast. That information went there, wherever it needs to be processed, and I needed to pull back. Okay. You want to make the pulse travel faster, it's going to cost you more. You want to spend less and make the pulse travel slower, it's going to burn you. Okay, so that's how you decide on the speed. It's a cost-benefit analysis. Okay. So that's the speed of the thing. And the strength of the signal is conveyed by the number of pulses transmitted. What does that mean?
Well, you hit something, a lot of signal, something that sends a lot of signals, you'll feel it.
So if it's very hot, then there are 100 pulses going a second. It's not as hot, 10 pulses a second or so. You eat high hot, 100 pulses a second. You eat mild food, 10 pulses a second. Okay, so that's what we mean by that. All right, so strength of the signal is conveyed by that. Okay, so we are going to learn how this thing works, okay? So this is the neuron body, dendrites, axon, and these guys connect to these guys on the next one. Okay, so that's the interconnection. So there's the axon that's inside the cell, and these are sort of myelin sheets, and that they're sort of energy preserving devices. The nerve impulse will jump across that. Okay, so anyway, these save you energy. So if those sheets go bad, there's some kind of disease. Is it ALS or
Polio.
no? Okay.
The polio destroys myelin sheath.
Okay. All right. So if that's destroyed, there's another one as well. Well, it takes a lot of energy, so you're always tired. Okay. So,
Lots.
huh?
Is it lots?
No.
You spell it?
And I know the name to do that.
Well, no, but how do you spell the sheets?
Myelin sheath. MYELIN.
Multiple sclerosis.
Oh, there you go. That's the one. So we'll come to that. I'll tell you a number that's kind of mind-blowing. Okay. So this is inside the neuron. This is inside there. Okay? Inside the axon. Well, inside any cell, what you have is potassium ions and large negative ions. So this is what makes it neutral. So these are the stuff. And this is the cell wall. And this cell wall is permeable to potassium ions. Okay? Outside, what is inside? What is outside? You know, we've all evolved in seawater, so essentially outside environment is sodium chloride. So under normal resting conditions, the wall is permeable to potassium ions. It doesn't let any of these large ions go out, and it's impermeable to sodium ions. All right, now diffusion, you guys know diffusion, if you have a permeable membrane, and if you have a higher concentration, these ions would go out, will migrate out, because the higher concentration, there's a, diffusion, these will diffuse out. What stops them? Okay, so they'll diffuse out, and this becomes negatively charged because this was initially neutral. A bunch of these guys diffused out, this becomes negatively charged, and the next one trying to go out is being pulled back by this guy. Okay, so the diffusion force is being balanced by the electrostatic force. And what is the equilibrium state? You get enough of these going out where the equilibrium state is you have minus 70 millivolts inside. Okay, so that's what's the diffusion state. All right, so now there's the axon. Everywhere along the axon, it's minus 70 millivolts. Okay, now we're going to do the following. We're going to pinch you or something like that here. We're going to do something where we're going to alter the properties of the cell wall at that location. Okay. You alter those properties of the cell wall, and now it becomes permeable to the sodium ions. Okay. So remember, this was negative, so the sodium ions run in. They have a higher concentration here, and in addition, there's an electrostatic attractive force. There's a whole bunch of them that'll run it. It's like, offering free beer on a college campus. Oh, man. So at that location, from minus 70 to plus 30 millivolts. Okay. And soon as this became positive, remember, now it's more permeable to potassium ions, and so these guys go back, so you get a nerve impulse. Okay. And now this guy's changing the properties of the neighbor, and so this will propagate. Okay, so this nerve impulse will propagate. And how fast does it propagate? About 100 meters a second. 100 meters is from here to the student center. All right, so in creating this, what happened? Remember, you got a whole bunch of potassium ion outside and sodium ions inside. You got to reset that. You got to put these sodium ions back there and bring these potassium ions back here. Costs money. 20% of your energy is spent on that. Yep. All right, so that's how stuff works. All right.